Right, welcome everyone. So it's time for the last sessions, I guess, because we're still running parallel. And first out, Robert Guthrie, right?
Guthrie, yes, yes. Thank you.
Do you let people know outside that it's started?
Yeah, I did let them know. Did they care? That is a completely different question. Might not have been enough coffee. Guthrie.
Guthrie, it's okay.
See, he's good with his face, I'm not. So first out is Robert Guthrie, and he's going to be talking about Yeppp.jl, or Yeppp in general.
Yeppp in general.
Take it away.
Okay. Hi, it's great to be here. I regret that I couldn't be here for the rest of the conference. I had to fly in really late last night. And there was also, I think there was a talk on Yeppp, it wasn't on Yeppp, but it included Yeppp earlier today, which I didn't get to see. But so maybe you already know a little bit about it. I'm mainly here just to tell you about what Yeppp is, how you can use it, and then go into some of the details about optimizations in Yeppp kernels. So basically, Yeppp is a vectorized mathematical library for a variety of platforms. Yeah, and then I'll also just go into some of the performance and things like that. And the main key point I want to make is in comparison to optimizing compilers like GCC, and in particular Clang, which uses LLVM, which powers Julia, you can get a lot of performance increase by just writing these optimizations yourself. And that compilers don't generate as good of code if you are careful with how you order your floating point instructions and things like that. Yeah, so Yeppp provides a lot of elementary functions. It's basically the building blocks of mathematics. So if you can think of anything that uses logarithms, cosines, exponentials, elementary arithmetic, max mins, whatever, you can do it, which more or less covers everything scientific computing related. There's also useful utilities for benchmarking programs, getting cycle counters, looking at CPU ID, things like that. And also, it can run on x86, MIPS, ARM, and on a variety of operating systems. And interestingly, it's written in Python, which is probably a little bit weird for something that runs fast and is more about assembly programming. But it uses this tool called PeachPy, which was written by a grad student at Georgia Tech, which is where I'm from. And yeah, it's a very nice tool. It's almost like using Python as a preprocessor almost. So every instruction maybe is represented by a class. When the class gets instantiated, it's added to some instruction stream. And you can do loops and things. And maybe you have like some sort of template for a function. So like an add function for a single precision and double precision is basically the same. You just have to use a different instruction for single or double precision. So you can maybe select that instruction as you're assembling, as opposed to having to write two big, long functions that are more or less the same thing if you're going to write them in assembly. So Yepp's past and present. It was started in 2011. This Yeppp info is our homepage. And the project originally started for research for high throughput computation of elementary functions, and this was the publication. And then in the future, we are working on mainly new configuration and build system because the old one was kind of slow and hard to work with. And then adding library support for complex numbers, AVX 512, which is something I'll get into in a bit if you haven't heard of that, and then more mathematical functions, and then also single precision transcendentals. So I'm going to go over some performance benchmarks that I ran. These are on an Intel Haswell 4770. Those are the compiler flags. I mainly compared to, like I said, Clang and GCC. And I know there was a question earlier about Clang or LLVM generating SIMD instructions, and so I'll go into that a little bit also. And so here's achieved throughput on evaluating a polynomial. So say I have some polynomial, maybe degree, I think I ran it with degree 100 or something like that. And I want to evaluate it on some vector of, so maybe I have 1,000 elements and I want to evaluate the polynomial on each of those inputs. And so here's the achieved throughput for that Yeppp has. Mainly this comes from things like fuse, multiply, add instructions and being clever with things like that. And GCC and Clang, as you can tell, don't generate very good code for this. the implementation in those was just a typical Horner scheme evaluation. And here's a cycles per element on dot product. And again, Clang and GCC don't generate very good code. They vectorize, but in particular, they're very bad at hiding latency, which is going to be the main focus of what I talk about when I talk about optimization. And so why is Yeppp important? Why is low-level optimization important? Because I think that maybe not in crowds like this where people care a lot about speed, but typical computer science majors or people that go do web development or something like that maybe don't care a whole lot about speed. And they think, oh, Moore's law, things are going to get faster. If I optimize for Haswell, it's going to come out like Broadwell comes out or Skylake comes out, and it's just going to make it irrelevant. But that's not really the case. And I know it was mentioned earlier that you can't really increase clock speeds anymore. So where do we get more execution as far as single core is concerned? So there's the option of parallelizing everything, but we're not concerned about that. We're concerned about single core efficient, high throughput computation. And so the answer to that is things like SIMD, FMA, and that's where most new performance from floating point computation is going to come from. So if you're interested in making things run fast, you can't just sort of write code and it'll be fast when the new processors come out. You have to take care to use the features and use them well. And so I'm going to talk a little bit about why Yeppp outperforms optimizing compilers and the main optimizations. So I'm going to start with this very simple loop in assembly, which just adds two arrays element-wise. And so as you can, is basically vmove scalar double, so adding two double precisions, load them into registers, add them, move them into the result, the output, and then add an offset. So one element at a time, it moves into the registers from memory, adds them, and puts them back. And so this is obviously going to be very slow. All the instructions in a row are very dependent on each other. And I computed that this had about 0.633 GFLOPS, which is low compared to what you can get. And so the first thing you need to do is you need to use SIMD instructions, which have been mentioned a lot. And modern SIMD instruction extensions are very complex. There's a lot of options, and it's a very varied history. Actually, I have a graphic of the relationship of different instruction extensions. But yeah, I think most people are probably familiar with the idea, but I just want to mention it again. It's single instruction, multiple data. I have maybe in the newest one, AVX 512, you could do 8 double precision floating point additions in one instruction, let's say. But those are in Knight's Landing, which are sort of higher end, and maybe a lot of people aren't running that. So in Haswell, Broadwell, Skylake, it's 4 double precision floating points per instruction. And so here's a relationship. As you can tell, that SIMD, I think MMX is the first one, which was multimedia extensions, came around like the late 90s, I'm pretty sure. And then it just branched into a whole mess of different things. And since Intel has to have backwards compatibility for everything, they're all still there. And so SSC, streaming SIMD extensions, and then AVX are the newer ones, which is advanced vector extensions, I'm pretty sure. And then also FMAs, which are fuse, multiply, adds, instructions that could say the output would maybe be A times B plus C or something. That could be done in one instruction. And here's another just little graphic of SIMD instructions, but I think that they're more or less pretty clear. You just have to, you can load a vector load into a register, 2 different arrays from memory. You add them in one instruction, and then the result is output into this register. And so I just added SIMD instructions to that loop that I had earlier that was just doing one thing at a time. And again, so that's 4 operations. 4 operations per instruction, but it didn't quadruple performance, right? So it was even less than double, I think. So why did it not improve performance 4 times? If I'm doing 4 times the work per instruction, it shouldn't really matter, right? But the main problem is latency. And so earlier, during the last talk before the break, the gentleman was talking about how to hide latency, you'd want to just have more work to do. So in GPU computing especially, if you want to ask the question, can I spawn more threads for this problem, the answer is probably yes, because those long latency memory accesses can just be masked by scheduling more threads or something like that. But again, this is single core optimization. We don't have the option of spawning more threads. And those floating point instructions have latencies, and they don't execute immediately. So for instance, floating point SIMD adds maybe about three cycles of latency. And again, in this loop, everything is dependent on the thing before it. And so there can be no parallel execution. But the answer to that is here's another demonstration of the difference between just that plain vanilla loop and SIMD and cycles per element. So again, it was only about twice as fast despite doing 4 times the work per instruction. So then the way to fix that, at least in single core optimization, is software pipelining and loop unrolling, which are, I think software pipelining probably dates from like the 60s, but it's only gotten more important as Intel processors have very deep, very complex pipelines and parallel pipelines. So for instance, you could execute more than one floating point instruction at a time, provided that they're independent of each other. And so the idea of software pipelining is to interleave. So one iteration of the loop, let's say, will read in element I from your first input, read an element I from your second, add them, and then store them to element I, increment the loop counter, and then do that again. But that's just slow, and there's a lot of overhead. And so here's the idea of software pipelining. At the very top, we have that basic loop iteration that I just said. So you just load, add, store, increment, load, add, store, increment. So one way to improve that, at least to get rid of all of the loop overhead of incrementing the index so often, is to unroll, which is a really common thing, and your compiler can do it for you, which is basically, instead of iterating or incrementing after each iteration, you would instead just do, like say, in this case, it would be three iterations for every increment. So you're doing a third less work as far as loop overhead is concerned, but still, actually I should say that these instructions are being executed left to right and then top to bottom. So in the middle part with the loop iteration, see LD, XI, add, X, or add and then store and then load, add, store, like that. So yeah, but with just loop unrolling, you're not really hiding the latency, right? Because you're going to be executing the load for element XI, you're going to add XI, and then you're going to store that result. And that's all going to be dispatched one after another, and those all have to wait for the previous instructions to finish before you can do anything. So the idea here with software pipelining is to schedule your instructions so that whenever you dispatch an instruction, the result that is needed for that instruction to execute is already there. So it more or less works like a pipeline in a processor, and it plays into the strengths of the pipelining in processors so that you don't have big, long pipeline stalls and things like that. And so this is actually a really, really effective optimization because instead of stalling the pipeline has to wait for, okay, this instruction has to finish before I can do the addition or I can store the result. You can see that there'd be a long distance between, say, like when you would add y0, x0, y0 equals x0 plus c, but you would store that maybe 3 instruction dispatches later. And so the result of just that optimization was pretty large. You can see that the achieved throughput on that was a little bit over 10 gigaflops, and the vanilla and SIMD loops were more or less not effective at all compared to that. And it all has to come down to making sure that you're not stalling the pipeline, essentially, and that you're hiding the latencies by unrolling the loop, and that instructions can be dispatched and executed quickly. And again, here's cycles per element for the same thing. And once again, the pipeline loop gets about 0.25 cycles per element, which is pretty fast. So then I also want to talk a little bit about high throughput transcendentals, which was more or less the main focus of Yeppp. There's a lot of things you can do with them. There was the options Black-Scholes example earlier, which I was going to use. The modern 2016 market moves in microseconds, and that's why like this sort of speed would be important. Black-Scholes involves logarithms, and you have to compute a CDF of the normal distribution, which involves exponentials. And so you might think with high throughput, oh, I'm just going to use a GPU or something like that. But let's say with options, then maybe there's only 5,000 different options available on American markets. So that overhead of transferring to a GPU to do that computation just isn't really worth it. And you're also going to probably be doing that computation millions of times a day if you're trading options. So the more effective way to do it would be to do this very quickly on a CPU so you avoid the overhead of transferring data back and forth from the GPU and the CPU, since you're not transferring enough data for that overhead to be worth it. And so there are three main things to avoid when implementing high throughput transcendentals. You might want to do these things if you wanted to just do a low latency transcendental. So for instance, if you're trying to compute like an exponent, you would want to do table lookups because they're going to be faster. But for high throughput, it's not going to be the case. So I'll go through these three things and sort of explain why that is. So unpredictable branches, branch prediction has gotten very good, and the cost of missing a branch has only gone up. Like maybe 20 years ago, missing a branch didn't have as big of an impact on your floating point throughput as it does now. It has a huge impact. And it's very important that you don't have a lot of branches in your code that are going to get missed. And so an unpredictable branch would be something like if I branched on a random number generator between 0 and 1 uniform, and the first branch was it's less than half, and the second one is it's greater than a half. Like almost by definition, that branch is not going to be predicted well at all. You don't have to do that in exponentials, but that's just an example. But avoiding them is key to keeping the pipeline going smoothly. So if you miss a branch, then all this extra work in the pipeline just has to be flushed and forgotten. And I think in Haswell, which is what I benchmarked on, a branch prediction miss might be like a 16 cycle cost or something like that. But it has a big impact on your throughput, so that's something to be avoided. Although, of course, branching on like special cases, like an input to the logarithm is -1 or something, like that's not going to work. That's fine to have a branch on that because you can expect that the user's not going to pass in, like half the inputs aren't going to be negative, and that's going to be a very predictable branch, and the cost is going to be more or less non-existent. Table lookups. So I think the classic implementation of something like in libm, like Apple has a very good open source implementation of like low latency exponentials and things like that if you want to look at that. And those use table lookups, and that's totally fine to do if you're trying to do that. But if you're trying to do high throughput, so I want to compute a transcendental on 1,000 elements very fast, table lookups are bad. And the main reason for this is that there is a SIMD gather instruction. So I just put some inputs like indices into a table, into an array. I do the instruction, and I get the results of that table as the output. But that instruction is at extremely long latency. It's something like, depending on the data type, it can go from like 15 to 40 cycles. And it's very hard to hide that latency with software pipelining. And again, you're going to just have a lot of waiting around for results before you can continue to do computation. So it's important to avoid that. So I think the typical implementation would be something like you have your domain, so logarithm has its domain on the positive reals. You reduce that domain, approximate it, and then reconstruct back to the original domain. And people always use table lookups for things like that. And they're fast for one element, but they really hurt your throughput for these sort of SIMD calculations. And finally, avoiding floating point division, which is, I think a lot of people sort of know that division and modulo and things like that are very, very slow in hardware and have very long latencies. So again, you can't mask floating point division's latency very effectively. It's very difficult just because it's so long. So like in that software pipelining example that I had, you maybe have like maybe at most like 4 instructions in between 4 instructions dispatched in between when I start calculating a result and when I need it. And if your latency is 10, 15 cycles, it's still going to cause stalls. So those 3 things in particular are used in Yeppp and are very important for these high throughput transcendental calculations. And so, yeah, I think that's pretty much it. There's the home page, the Bitbucket, and there's also a link for PeachPy if you want to use PeachPy. I actually do want to show the PeachPy code that I wrote really fast, just because I think that it's interesting. If you're going to be writing like assembly kernels, it's a very neat tool. For one thing, you can almost write cross-platform assembly, which is a little bit of an oxymoron, but there's functionality like here. You load argument. This is sort of an abstraction for the general way of loading an argument from whichever ABI you assemble the code with. So if I assemble this with like sysv or sys5, however it's pronounced, it'll do that. If I use it with something else, it'll adjust it for the necessary way to load an argument for that ABI. And so, like I said, every instruction is basically just some class that you can construct. And the syntax is more or less exactly like Intel syntax for assembly. So that was just the vanilla loop. And then something that was really powerful about the tool is, so here's the software pipeline loop, which is way bigger and very hard to read compared to the others. So that was just the SIMD loop, few instructions, very clear what's going on. But the software pipeline one is pretty massive. You have to be very careful about these indices. And if you were doing this for a lot of different data types, you'd have to do this over and over. But you could actually pipeline loops algorithmically, which is what this function did. And that huge, massive loop that was totally unreadable can be done by just doing this, by just adding instructions. These are just the columns, like in the graphic I had, there was columns of different instructions that you were trying to do, and then that loop will that function will automatically interleave them and pipeline the loop pretty effectively. So this actually generates the same code as the other very long and difficult to read sort of typical assembly that you might see. So yeah, I think that's pretty much it. If anyone has any questions, or I think there was a lot of things mentioned earlier that were at least relevant, like Clang generating AVX instructions correctly. It does do that well, but generally it doesn't hide the latency effectively. So that's, yeah, that's pretty much it. So are there any questions? Not right now, but it's something that me and my advisor are interested in implementing. So it doesn't have one right now.
Any other questions from you? You said to avoid table lookups.
Uh-huh.
You didn't say like how.
How?
Yeah.
I mean,
If you're doing a log function, then you need to go the normal way we involve table lookups.
you could instead just do like some sort of higher order. I'm sorry. You could do some sort of higher order polynomial approximation. So typically, like in Apple libm or something like that, it'll be like a table lookup for very accurate for some parts, and then also like an additional polynomial approximation. So you can sort of use them in tandem, but for the SIMD table lookup instruction is just so slow and its latency so long that it's more effective to just do some sort of, like in your domain reduction, you're approximating it with some high order polynomial, and that's actually much faster. Like I showed earlier, the polynomial evaluation, if you're using like the more recent instruction extensions, for that, that's very fast, and it's faster than trying to do this big long table lookup. Or it's not faster, but it gives you higher throughput.
I have another question.
Okay.
Do the processors have any of this stuff in hardware already?
What do you
Do
mean?
they have anything which is designed for accelerating, like argument reduction for sine and cosine and stuff like that? Is any of that consistent in hardware?
I don't think so. I think, well, it might be that way. Like there's hardware instructions for like square root and stuff like that. I don't know if there is one for x, If there is, no one really uses it because all the libim implementations are things like I was talking about earlier. So not that I know of, but maybe someone else here knows. But
I was going to say, there is an extension to the Intel instruction set that has extensions for that, that's only on certain chips for targeting scientific computing.
okay,
I've seen
interesting.
something about like, some helper thing for art plans or something, or maybe it's a tangent function, but I don't understand why people would use it if it's available. Maybe it's just
Any more? Okay, thank you. Appreciate it.